the multi-valued stuff in the vertical direction, not in the horizontal as I do. And I'm happy to discuss it afterwards. Or you asked Danny or I want to explain that. Yeah. Okay, so just to make sure my picture was wrong, it goes vertically. Okay. Now I also want to just add with a few comments on the wrinkle submersion, what happens if we are not in the equidimensional case. Again, it goes from the n to WQ, and if we have n strictly given, then Q, then the proof for the case n equals Q fails, because the composition, the post composition of a wrinkle. So let's take an equidimensional wrinkle. That's what's coming up in the proof. So this is a wrinkle. And then, in fact, it already fails if you just take a projection here onto the wrong coordinates. So if we go to RQ and we take the projection onto the last Q coordinate in my local model that I wrote yesterday for the standard wrinkle, and if you just take the standard n-dimensional wrinkle and you project onto the last two coordinates, you forget the first coordinates, then this is a composition of a wrinkle with a submersion, but it's not wrinkled. You can work that out even if, say, if n is equal to 3 and q is equal to 2, it already happened. I think if n is 2 and q is equal to 1, it just barely still works, just by accident. But then for n equals 3 and q equals 2 already goes wrong. Whereas if you project onto the first two coordinates, it's fine. So this depends on how the wrinkle sits with respect to this projection. So the standard wrinkle is sitting in there, say like this, if I'm drawing the image of the wrinkle, and then I'm projecting onto the last coordinates, and then I'm looking at the fibers of the projection, then somehow here where the singularity is, it's becoming tangible, it's not transverse to the fiber. Whereas if I project it out the other way, it will transverse to the fibers, then it would be fine. Okay, so this is somehow what is, and then to remedy this, one needs two more things, which I'm not going to explain. One is chopping wrinkles. And this is something that I had mentioned already before. You can take a wrinkle and you can chop it into small wrinkles. So if you have a wrinkle which is big in the source and in the target, you can chop it so that both in the source and in the target, it's becoming as small as you wish. And this is so that you can localize it to wrinkles which sit with respect to the submersion that you have in a particular way, that you can somehow, that the tangent directions don't vary all that much, and you can somehow put it in a standard local model. But then it might still be this kind of local model where it's not quite working, and then you need to do one more thing, and that is very similar. That's corrugation. Very similar to what Melanie has been explaining, namely you really add some corrugation function onto this wrinkle. Somehow you start corrugating it like crazy. And then when you compose with this one, you can actually show, you can arrange that after you do such a corrugation, then the project, you will create lots and lots of wrinkles now for this composition. And then they will actually be wrinkles if you compose with this submersion. So, and that's somehow, that last part I find is some of the more, is maybe the most technical part in that, because you write down an explicit formula, you corrugate again with some periodic function and with very high frequency, and then you just need to compute it works. And it's kind of lengthy. Okay, so this was just maybe to wrap up. There's additional things that need to be done, and now in this talk, I want to talk about the case where Q is equal to 1. So we actually will need all that. So we're really in the extreme case where it's not equidimensional. Okay, so this will be about generalized, or let me say, it's Igusa's theorem, or maybe theorems for generalized Morse functions. So this H principle for wrinkled submersions already gives some kind of answer, because wrinkled submersions is the same as generalized Morse functions if the target dimension is a target manifold is just R. Yeah. So, but it's not yet a full H principle, as somebody pointed out. It only works if your manifold has 0 Euler characteristic, because we start with something which has the formal data already of a submersion, and if it has boundaries, say we assume it's already a submersion near the boundary, and they want to extend it inside, and we can do it as a wrinkled submersion. So it's kind of an H principle, but it's not yet a full H principle. For a full H principle, we really would want to say we take an arbitrary manifold which might not have any formal submersions even, but it has the formal data of a generalized Morse function, and then we want to say we can get from the formal data to the actual data. Yeah. So, okay. So we know what generalized Morse functions are. Now to formulate an H principle, I will do it in the foliated case. I had already said that you can incorporate parametric versions by talking about it in foliated case. Now in this example, let me actually do it, so you see it also for once how to actually talk about parametric versions. So the setup will be the following. We have W, an element manifold now, which will be of dimension k plus n, I think. And we want to talk about functions I will call phi to R. And this will carry an n-dimensional foliation. Let me draw a picture. I will add some more stuff to that picture. So we have this W, dimension n plus k, and we have a function phi defined on this, and this is the fibers of the n-dimensional foliation. And we are thinking of this as a k parametric family of functions on an n-dimensional manifold. Yeah, if we just restrict to the leaves of this foliation, then it means that every leaf is some n-dimensional manifold, and this is some k-dimensional parameter space over which this varies. Okay, so what we want to do is we want to take just the differential of its restriction to the leaf, and we want somehow its restriction to each leaf should be a generalized Morse function, right? So then let's say we call this a foliated or a leaf-wise. And instead of generalized Morse, I will just call it an Igusa function in honor of Igusa. So a leaf-wise Igusa function. If this function to each leaf is generalized Morse. Okay, so then now let's think what is the formal data. So let me actually try to be precise about this one. So what is the associated formal data? So first I will just derive it here, and then I'll make a formal definition of what the formal data is. Well, okay, well, we have the function itself, and we take the first derivative. So, and we should take the derivative in the fiber direction. So we restrict to the fiber and then take the derivative. So that means it's something which is going from the tangent space to the fiber. Well, yeah. So it's a linear map on the tangent space to the fiber, or I could just say it's a tangent space, the fiber, and then the dual of it. Yes. Now, it will be convenient maybe to pick a Riemannian metric on W to just identify it with a tangent space to the fiber. Yeah, it's a linear map from the tangent space to the fiber to R, but we can just identify it. It's like the one form with vector fields as formal data. So this is just the zero derivative. Now, okay, if it were submersion, then the zero derivative would be nowhere zero, it would be done. Now, it's not a submersion, so it has critical points. So let's say V, or maybe it's V of this function is where this is zero. Yeah, the zero set. And I will add it in the, well, I can maybe start adding it. Sure. Well, let me not yet do it. Okay, so this is where it vanishes. Now, so this is the set of critical points. So this is a set of leafwise critical points, yeah? Now, at critical points, we have the Hessian. We have the second derivative. Actually, let me introduce the restricted bundle. So let's say vert is the tangent bundle to the fibers, restricted just this one. So this is just a bundle over. And then in that bundle, we will have now in the second symmetric power of that bundle, we will have the Hessian. So which means I will write it as the leafwise second differential of phi. This would be a quadratic form on the fibers of this bundle. But again, I can also, by using the metric, convert it into a linear map from this bundle to itself. So I can view this as something which is self-adjoint with respect to the metric. Yeah, symmetric linear map, rather than a quadratic form of the same once we have the metric. Okay. Now, if this were everywhere non-degenerate, so meaning an isomorphism fiber-wise, then it would be a Morse, on every leaf would be a Morse function and would be done. But we have it generalized Morse, so this can still be zero somewhere. Yeah. So let's say sigma is the set, the point of V in V. So it's already critical points where the second differential is degenerate. That's not an isomorphism. So this is a subset of B. Yeah? Okay. So this is where the second derivative vanishes. Now, we know then, because generalized Morse means that then the rank drops by just one, which means that it has precisely a one-dimensional kernel. Let's call this lambda to be the kernel of this one. That is a line bundle over sigma. Yeah. So this only exists where we have a kernel, but then the kernel is just one-dimensional, and that is a line bundle over sigma. And now we have one other condition, namely that in the direction of that bundle, the third derivative does not vanish. So we have this the leafwise third derivative. So this goes from lambda to R. So this is a non-zero cubic form, which you can also, which defines you some, it's a cubic form from R to R, which means that one on one side it's positive, on the other side it's negative. So it defines you a trivialization of this bundle. So it defines you, and or otherwise I can take a section of length 1 in that bundle in that geometric anyway. So lambda plus a unit section in lambda. Okay? So that's it. This is the formal data. Now, and a priori, there's no reason why V sigma should be anything nice. Yeah, they could be horrible subsets. Now, generically, we will have that V is a manifold of codimension n, so of dimension k. So V is a k-dimensional manifold. And sigma is a k minus 1 dimensional. But you can work out the dimensions somehow. So, and in fact, the sigma is precisely where our manifold V is becoming tangent to the triangles. So this is where the sigma is. And then over sigma we have this line field lambda, and it turns out the line field precisely points in the fiber direction, and it's precisely the intersection of the tangent space of to V with the tangent space to the fiber at this point. So it's really looking like this. This is the lambda over sigma, and we have some orientation of this. We have some unit fields in there. Okay, so this is what it looks like. This is the associated 3-jet data we get from leafwise generalized most function. Okay, now let's just make a definition. What is the formal data of this one? So formal leafwise Igusa function. And the good thing of using Igusa here is that we can abbreviate, right? It's becoming pronounceable. So formal leafwise Igusa function is the following data. Let's say capital Phi to the huge from little phi, which is an actual function. So it should have, well, should have 0, 1, 2, and 3 third derivative data. And you just copy over. So let me just be very quick. So first of all, this phi 0 should just be a function on W. I mean, this homotopically carries absolutely no information. That's the function to R. That space is contractible, so we can actually forget about this one. Yeah, so we're not including it in the formal data because it carries no information. So the first one, phi 1. So this is again on this foliated manifold W with the foliation, right? Yeah. So phi 1 is now a section in the bundle. Then to this we get a 0 set. Then over this we have a vertical bundle. And phi 2 is from the vertical bundle to the vertical bundle family of self-adjoint linear maps. On that, sigma is where phi 2 is degenerate, and then we have lambda in the kernel of phi 2 and the bundle over sigma. And finally, okay, I don't want to write phi 3, let me just call it lambda plus is now a section, a unit section in this line bundle. Okay, now what? So this is okay.
And I guess you want to demand that phi 2 only degenerates in rank 1.
Yes, right. Phi 2 only degenerates in rank 1. Yes, and this is like only only for rank 1. Yes. Yeah. Right. So that you only have this one-dimensional kernel that's somehow implicit in writing that. Yes. Okay. So what does it look like generically? This formal data, you can still say, okay, we just take this formal data and make them generic. Right? What do we get? Well, still, this is a section in a rank n bundle. So it's 0 set generically, is cut out transversely, and it's a v-dimensional manifold. So again, V is a k-dimensional manifold, and sigma inside of here is a k-1 submanifold. But what we do not have anymore, now let me draw a picture for the formal data. So this still, and this V still looks something like this. But the sigma has no relation now to tangency of V with the fiber, because somehow sigma is determined by this second, where the second part is degenerating, and this has nothing to do with what the first part is doing. So it's absolutely, yes. So we have some sigma somewhere here, whatever, right? So the sigma is not where it's becoming tangent to the fiber. So we have no information about tangency of V to the fibers. Maybe I should have added here also that the picture is as I drew, that along sigma you see a full type singularity here, really. And here also maybe yeah, it's hard for me to draw something which is not full type, right? But I mean, not only is the tangency to the fiber not happening at sigma, it's completely unrelated, but also it has no reason to be folded here, really. Yeah. Okay. So now, but still with this data, I can state the theorem. It looks like 84 is every formal leafwise Igusa function P on W F. Let me state also the relative version, which is holonomic, meaning it is the 3-jet. I should maybe add, I think it should be here. Yeah, so P is holonomic. If P is what you get from an actual function, from an actual leafwise Igusa function. Yeah. So which is holonomic on an open neighborhood of a closed subset is homotopic rel neighborhood of this subset to a holonomic one. And this is a precise statement of the relative and parametric H principle for generalizing this function. Any questions?
Is A right?
A is a closed subset. So any closed subset, yeah, where this is already holonomic, then we can leave it untouched. So the proof consists of reducing it to the statement of wrinkled submersions, which we have. But there's some work to be done to get there. So for the schedule ideal proof.
Right, a bit confused. This is a parametric statement because that's his variation after that.
Yes.
But then he goes only proof is in a range or something.
I think he had some condition.
Yeah.
I think he had some condition which somehow one didn't need. I think.
Okay.
Yes. So yeah, I don't know exactly what it was, but I think there was some.
Map is like
There was some condition in his statement. Yes. Yeah. Maybe before I do it, because I wanted to mention that there's another theorem which I will not talk about because I will not have time. Which was also proved by Igusa 3 years later, or at least published 3 years later. And there is a framed version of this one, which I think topologists prefer because somehow then you get rid of topology. Yeah. So every I don't even have to talk about the formal data in that case because they automatically exist. So I can just say every framed, and I'm not going to say exactly, I will say a little bit what it is. Every framed leafwise. Yeah, okay, leafwise Igusa function, which is defined just on an open neighborhood of some set A, can be extended to the whole space as a framed function. Extends to a framed leafwise Igusa function on all of W. So there's absolutely no homotopical condition. So I can, for example, if W is something with boundary, I can take something which is already a nice framed Igusa function near the boundary, and then I can extend it to the inside. No homotopical obstruction. So part of the statement is that the homotopical obstructions vanish. So you can think of this one is this one plus the fact that the formal obstructions vanish once you add a framing. And just one word, framing means you pick trivializations of the negative definite bundles of the second differential. So if I go to this, for example, so we have the second differential, which is some self-adjoint linear map that has positive and negative eigenvalues. So you take the space spanned by the negative eigenvalues. So that's some subspace that defines some subbundle. And you want all those subbundles to have trivialization. So your data of a framing is trivialization of all the negative definite subbundles. You know something in Morse theory or Morse homology, somehow the data to define orientations on a Morse complex is you orient all the unstable manifolds of the critical points. So it's kind of similar here to you. But here we actually choose framing, so trivializations of the negative definite bundles. And you need to do it consistently over the locus where the index changes, because somehow the number of negative eigenvalues changes as you vary on V and you cross through sigma, where you, then it jumps, and you want some of these trivializations to be consistent in a natural way over where you have these jumps. But there's a natural way to say what it is. And then once you add these conditions, then somehow there's no more formal data. The formal data is contractible. So you get an absolute statement. So this is just, but I will focus on that. So let's look back at this situation. And the trick is that we first want to arrange everything nicely in a neighborhood of this singular set V. And then outside of V, we are in a situation where we can apply the Wrinkle submersion theorem. So we want to somehow make it in a neighborhood of V, we want to make it look like the an actual leafwise Igusa function. Okay, now a priori it doesn't. So now, okay, what could one do? One could now try to isotope this thing so sigma becomes the tangencies and also the tangencies become a folder. Now that seems very difficult to do because we don't really know what it looks like. So the trick is the following, that we're going to change the foliation. So we're looking at this V. Inside we have this sigma, this codimension one submanifold, and we want to have our folds at sigma, as in the picture, which you don't see. Right? Yeah. So let me put this one up. Okay. So let's just change our foliation. Let's take near each sigma. Let's just write the foliation so that this V near sigma looks like it's folded with respect to that foliation. Okay. So I take a foliation which looks like this nearby. Then when you follow sigma, this is folded with respect to that foliation along sigma precisely. Okay. And likewise here, we can choose a foliation like this, so that our V is folded along sigma with respect to this local bit of foliations. Now, you see, the local data is really just some, what I mentioned, one submanifold in a k-dimensional submanifold. Locally, you can write down some foliation where it looks like this. Yeah, there's no function to do that. Now, what is more work is to show that you can globalize this. But to globalize this, we're actually not going to be able to extend these local things as a foliation, but we are going to be able to do it such we can extend it as a distribution, which might not be integrable. So we need to generalize slightly our notion of this formal data. So let's say if theta is a possibly non-integrable distribution, a rank n distribution on W. So it's not a foliation, but it's just a distribution which might not be integrable. We define a formal leafwise booster function. Well, leafwise is not so great because it's not leaves, it's not a foliation, but let's keep that name anyway and just maybe put a zeta in front to remind ourselves that now it's with respect to a maybe non-integrable distribution. But if we look back at this definition, we see that everything makes sense if instead of f you put some distribution. We hadn't used integrability anywhere here. Yeah, so you can just write down the same thing and it works for a distribution. And then we'll say that this, so let's say phi again, and we say that this data phi is holonomic, or let's actually say it's locally holonomic. If on a neighborhood of V, which is the vanishing set of the phi 1 part of this one, where this vanishes near this manifold. Zeta is integrable and phi is holonomic. So because to say what it means to be holonomic, well, one can also say it for non-integrable, but we don't need to. So we assume that near the set it's already integrable, and then we know what holonomic means. Yeah. Okay. Now I can state the first step in the proof, and that is we can find so given a formal device function phi. So we start with the formal data. So now I'm back with my original foliation. Now we find rank a homotopy of rank n distributions zeta t such that zeta 0 is say zeta and zeta 1. I will want to do it, I think, that way. So this is the one coming from the foliation. So you find such like this. And a homotopy of formal leafwise Igusa function with respect to these distributions from this one to a locally holonomic. So zeta is the one I want to add up with zeta. And let's say we put that. So that means that for my I can extend this somehow as a distribution everywhere. That will be my new zeta, such that in fact the V is still the same. I haven't changed that, which is now the 0 set also of the new one, and then it's here it's already well, actually near all of V it's already holonomic. Yeah. Okay. Now we need to get back from this. Okay, then step. Okay, we can make all the ft integrable on a neighborhood of this one. So let's maybe call this W. I fix some neighborhood of these. So on that neighborhood, we can make all of them actually integrable. Okay, now I want to pull back these new local foliations. So I have now some neighborhood. This is now my omega. On this we have foliations, and I want to pull them back to the original foliation. So this is now, and this is now a problem which is in general not so easy to solve. So the situation is that follows that we have some manifold, and we are locally on a neighborhood of this submanifold. So this is a schematic picture. This is V, this is omega. Now the F0, so F0 will be the restriction, the psi t integrable on this neighborhood, and I will call them ft on this neighborhood then. Yeah. So so now we have F0, and that is a nice foliation for which this is folded. So this is folded with respect to F0. So F0, okay, maybe I should have rather drawn the foliation F0 nicely, and then draw this to be folded. Yeah. And now we're deforming F0 through some FTs, some foliations nearby. And we want to, what we want to do, we want to keep the V folded for all these foliations. So we want to carry along V with its homotopy of foliations so to some VT, which are always folded with respect to FT. So this is the second step that we want to do that. And this is not obvious, and it cannot directly be done. It is possible after introducing additional folds in V. So as it is, it might not be possible, but we can do some kind of, we add a lot of additional folds here. And once after we did that, then it becomes possible that we can follow this homotopy of foliations to keep it always in folded position. So this is non-trivial. This requires wrinkled embeddings, which I did not have time to talk about. So this.
Can you recall? Excuse me. Can you recall what is the codimension of the FT with respect to the dimension of V?
Yes. So they're complementary dimension. So they're complementary dimension. So V is k-dimensional, and they have codimension k. So it's exactly that generically you're transverse to the fiber, you're intersecting fiber in isolated. Yeah.
Can you give an example to show that it's not in general possible without introducing more folds?
No. I don't. Yeah, I try to think about it, but I don't know. I don't. Yeah. So this uses wrinkled embeddings. So there is another H principle with wrinkles about wrinkled embeddings rather than wrinkled submersions, and that is being used here because you think of this V as being embedded, and you want to make it wrinkled with respect to the foliation, and and then you get, resolve the wrinkles into double folds, and that's how you get this folding result. Okay, once we have that, we can now the VT, they are just an isotopy of these submanifolds. So I can write the VT as HT of V for some for some ambient isotopy of diffeomorphisms. Yes? So for diffeos HT on W, starting at the identity. And now, instead of saying these foliations, okay, actually, and I can in fact arrange that HT is the identity outside this neighborhood here. Because everything will actually happen in this neighborhood where everything is integrable, where there's distributions and foliations. Yeah. So I can so now you can, instead of having these foliations move and the submanifolds move with them, I can pull back everything under this ambient diffeomorphism. So after pulling back Ft and dt by ht, we are now in the situation that our original V is folded with respect to our given foliation. So remember, we started with some formal data, which had some zero set V, which was in no particular position with respect to the given foliation. But now after that, after we pull back, I can assume that this zero set is in folded position with respect to this one along sigma. So the picture looks like it should for near V. It looks like it should for leafwise function. So it's really looking like this now, where this is sigma. This is V. Now comes the last step.
One question that,
Yeah.
so you're claiming that by the foliation moves also with this isotopy or what?
Sorry?
So you're producing the foliation FT,
Yeah.
with this isotopy HT as well.
This
It's
is
not that.
again.
Because it feels like what you're doing is like when you pull back the foliation FT, you get F, right?
Yes.
That's what you're saying.
Yes.
So the formation FT was already produced by this isotopy.
So the FTs came from this one. I produced a deformation of the original foliation through not foliations, but somehow distributions, but which on a neighborhood on this omega I can make foliations. And they start with the given one. So if I pull back because H0 is the identity, I get my original one. Yeah. Okay. So then let's look here. So step 3 is that once this V and sigma are in the correct position with respect to the foliation, and I have the formal data, I can write locally near V, I can write an actual leafwise Igusa function whose free jet is this one. So somehow this is now some just writing down things explicitly in local models. So we can, there exists now a leafwise Igusa function P on an open neighborhood of V such that its free jet, well, is at least homotopic to the given one. Yeah, might not be exactly equal, but it will be homotopic. And actually, I can do this whole thing fixed outside of the neighborhood omega. Well, anyway, this is, okay, I want to say I can do it relative to the boundary of this neighborhood so that it still extends outside as a formal data. No? Okay, so now what do we have now? Now we have we have this picture of W. We have our V, we have some neighborhood. And on this neighborhood, we already have our leafwise Igusa function. And this is where all the action happens. This is where the derivative vanishes, where maybe the second derivative has a kernel and so on, right? Now outside, we have still the formal data, which, let me remind you, it consists of a map phi1, some phi2, and some trivialization of some bundle. But this phi2 only exists over the zero set. So this is really just inside of this neighborhood, yeah, and this one also. So this is already just happening inside of here. This is no additional information. But what about this phi1? This phi1 was a section in this the tangent bundle to the fibers, right? And its zero set is V, which is also contained in this neighborhood. So this phi1 doesn't have zero. So it goes into this one minus zero, right? So this is the data of a non-vanishing vector field in the fiber directions, which is precisely the data for the formal data for a submersion. This is the formal data for a leafwise submersion. I mean, a leafwise, yeah, submersion. Wow. A real valued function which on every leaf doesn't have any more critical points, yeah? Because we have a candidate now. Okay. And now we can apply the wrinkled submersion theorem. And this means that I can turn this formal data of a submersion, I can turn it into a wrinkled submersion. So we can, and because here on omega, this was omega or neighborhood say, on omega it was already near the boundary of omega, it was already an actual submersion. I can keep it because I have a relative version, I can keep it the given one. So I can take the phi, which is only existing on omega, it extends to phi on all of W as a wrinkled submersion outside omega. So, which means that outside of omega, we're going to have additional wrinkles. And so it's not going to be in submersion, it will have wrinkles where here the differential vanishes and here the second differential vanishes. But we already convinced ourselves that a wrinkled submersion to R is nothing else but a generalized Morse function. Yeah. So. Okay. And now, of course, I haven't been very careful keeping track of the formal data all the time. Now you have to trace that all the time you carry. I said it at some moments, but I also say here, for example, you need to understand that when you introduce these wrinkles, somehow you do it being homotopic to the original given formal data. Yeah, so now trace the formal data with the proof and then it and that's okay. Thank you.
Questions or comments? So to me, it seems as if the data you have for formal leafwise user functions is significantly more complicated than in situations before we had. for example, you have a function that's only defined on a
Yes.
subbundle
Yes.
over a certain subset. So my question is maybe, is this also just sections of some jet bundle secretly, or is it more complicated?
It is phrased in the 3-jet bundle. Yeah, everything happening in the 3-jet bundle, but you're totally right that it's complicated because the various bits of data are only defined on certain subsets. And for the general definition, those subsets are not even particularly nice. They're just some closed subsets where the one vanishes and then you have this other data. Yeah. So indeed, it's kind of not so pleasant to talk about even homotopies of such data because you have to equip these data with a topology on the space of these data, right? Now, if you think about it, because when these data vary, then these subsets might vary, and it's not very easy to say what is even homotopy of data and how to even say that these formal data are homotopic. Yeah. So in the book, we kind of wiggle our way around it by doing the following. We actually prove the framed Igusa theorem, the second theorem that I stated, which is not having any formal data, and then indicate how to deduce the other one from that one. Yeah. So somehow then we don't. So the framed Igusa theorem in that sense is easier to prove because for that you don't need formal data because somehow they are not in your way anyway. Yeah. So you just do it directly, and then you can actually deduce the other one from the framed Igusa. But otherwise, yes, you're right.
But say in the unfolated case, you could probably define a space of formally Leaf-wise Igusa functions. And is this space sections of some bundle over my source manifold?
No.
Okay.
No. I mean, the formal data isn't. I mean, the actual leaf-wise Igusa functions. I mean, the holonomic ones,
Yeah.
they are, of course, right? They're just functions satisfying some conditions. So there is a very nice and clear space with some kind of functions with the C3 topology, say, and conditions on the first three derivatives. But the formal data, no, because some of these sections are only partially defined on some subset. And unfortunately, those subsets need to be allowed to vary also, as you talk about homotopies of these data. Yeah. So they are not. No, they are not. No. It's a more complicated thing to talk about.
I'm not sure if I followed your second step, but I'm wondering if when you add that wrinkle embeddings and that possible extra folds, when you finish this step, is the previous sigma the one that where is folded?
Okay. Good point. Okay, so for the F0, this was folded along sigma. Okay. Now, okay, when I introduce additional folds, then I need to change my sigma. So I'm changing my V by wiggling it to some V tilde with additional folds. And I also need to change sigma to some sigma tilde, which in fact will be the original sigma plus some other parts coming from here, right? So I will have to increase it. And then again, I have to trace the formal data. So the formal data is not changing because, yes, and I have to show that it's still the same formal data.
It's not appearing in the new sigma tilde, that line bundle from this stuff.
Sorry?
Are there formal data in the new sigma, in sigma tilde?
Well, they are part now again of the new formal data. Yes. Yes. Okay. But I need to show that they are homotopic to the original one.
I see.
Yes. But because the folds are created as double folds somehow, and the sigma appears in pairs of parallel copies, and therefore you can somehow show that the formal data can be homotopy back to the original one. Okay. Yeah, it's changing.
Is that also how the original proof was?
No, I mean, I actually did not study Gusta's proof, but pretty much certainly not because wait, Yeah, no, at that time, the wrinkling theorem was not available. So, yeah, it was not.
If I specialize the Agusa theorem setup to one parameter families of Morse functions, I'm wondering what is the relationship to surf theory?
So surf theory tells you how the critical values change in families of Morse functions, right? And yeah, I don't know whether I can say anything meaningful about that. So somehow it seems the critical values of the function don't play a particular role in here. I mean, in surf theory, like critical values crossing and so on, all this you see in the surf diagram, and it doesn't play a particular role here. So we're somewhat, you see, I never really cared about the actual values of the functions. I only cared about its derivatives, second derivatives, and so on. So I think that part, but I mean, there might be something. I think you could now combine this and look also at the surf diagrams, and it should tell you something. But I don't know a good answer for that. I don't.
If I were a great person, could I do something similar for maps to R to the K with moderate singularities instead of to R with these techniques?
Well, I think in principle, yes, except as you see, I mean, this is indeed now, of course, the disadvantage of this more explicit approach is that we really need to somehow spell out explicitly the formal data. And now if you have a map to RK with some kind of singularities, that's going to become more complicated, right? And somehow you see that here really the formal data, they somehow carry their own geometry because you have this vanishing set V, and it's important that we can put this into some folded position with respect to this foliation, which is really a non-trivial result. So I don't know what would come up if I look at other situations. Yeah, in the formal data, there might be some things that get in your way that you need to somehow put into some nice position that might require some actual theorems that we don't have. I don't know. I don't know that. Yeah. So we would, I think, with this approach, one would have to do it case by case. Like for another case, we would have to look what is happening at the formal data and how to standardize everything there. Yeah. And somehow I find it a bit discouraging, the fact that here already in this simple situation, we encounter an actual difficulty in this formal data of somehow following a homotopy of foliations by keeping some manifold tangent to it, which is non-trivial and requires a whole new set of results. Yeah. So I don't, yeah. I'm a bit skeptical. Probably one could do something, but it would be getting complicated.
Let's think on it.